This video is entitled Intro to Functions of Several Variables. Now, throughout calculus up to this point, we've pretty much just dealt with functions of a single variable, most commonly like y equals f of x or some other function name, doesn't have to be f, or even in terms of t, parametric, y as a function of t. But there's always been only one independent variable. Now we're going to look at the concept of functions where you have one dependent variable but two or more independent variables. Let's take a look at this. So for example, this one right here is z equals f of xy. That's telling you there's two variables in this function, x and y. So that means this equation part over here can be any combination of x and y variables only. And then here's some stuff like, so technically a volume of a rectangular solid is calculated as length times width times height. So that could actually be written like this as a function of three variables, L, W, and H. So L times W times H. Now here's one of a right circular cylinder. Volume as a function of the variables R and H, radius and height, would be pi R squared times H. So evaluating multivariable functions is pretty straightforward. You can pretty much see the ordering of the letters, and when you evaluate a function and a number, you can pretty much see what's going to happen here. So here's your function f of xy. And then, so if you wanted to find f of negative 2, 3, which essentially is the same as finding the z. So what we're doing, as you'll see later in graphing standpoint, you're finding the z value of a three-dimensional function, three space, based on two independent variables, x, y, and then you get your z. And I'll explain that after I do this. So this part's pretty easy. So you plug in negative 2 everywhere you see an x, and then you plug in 3 everywhere you see a y, and you get negative 21. So what I was trying to say about the graphing part of this is this three-space function right here would have the point negative 2, 3, negative 21 is for the z. That ordered triple would be on that graph of that equation. So anytime you plug in any two x's and y's, you'd get another ordered triple. So for example, 0, 0, you'd get 0. So the origin, 0, 0, 0, would actually be on that graph. Now this one, I'm just being a little silly here. I would not use this in the context of an exam or anything like that, but I just used three arbitrary symbols to represent the variables and wrote an equation. It would work the same way. So if you're going to evaluate f of 3, 4, negative 2, you're going to put in 3 everywhere you see a question mark. You're going to put in 4 everywhere you see this pound sign. And you're going to put a negative 2 in everywhere you see the happy face. Pound sign is what we used to call it. Now it's also known as a hashtag. But that's a symbol that I'm not sure if it's used much anymore, but it was always denoted in science as measuring pounds. So you plug the numbers right in there and you get negative 328. There you go. So that's pretty easy. Finding domain, I don't want to get these kind of questions to be too complicated here. But you're essentially looking for the same kind of things you would normally look for. You're looking for, you can't have divide by 0. You can't take the square root of a negative. You can't take any logarithm. You must be positive, not just 0. But that's the difference between a log and a square root when you're evaluating domain. As long as it's not in the denominator of a fraction, you can take the square root of 0, but you can't take the log of 0. It's got to be something larger than 0. Even 0.000001. Anything strictly greater than 0. And so for this one, I'm basically saying the domain is all x and y. There's just different ways you can write this. It's not that critical that we know a bunch of different notations. But this is saying all x, y, vertical lines such that, so if x minus y is on the bottom, that means x cannot equal y, because anytime x equaled y, you'd have 0 on the bottom. So it's that's as good a way to put it as any. As long as x is not equal to y, you're good to go. For this natural log one, because the natural log, the inside part has to be greater than 6. Well, I started out like this. The inside part has to be greater than 0. So and move the 6 over. There's no point in trying to solve for x or y separately here. That's not necessary. This is perfectly fine right here, but I went ahead and moved the 6 over just to show that whatever happens here, x times y has got to be greater than 6 for this to be a valid domain. All right. Looks like, you'll see what I did down here. These aren't very good. I should have used a smoother thing there to graph this, but this doesn't look too good, but that's all right. Don't worry about it. So this one's going to have a lot of places where the domain's not going to exist. So that's why it has to be x, x times. So obviously anywhere kind of right around the origin, the numbers are going to be too small because they won't multiply together to be greater than 6. So you got to get farther out away from it. And this domain that was up here was x cannot equal y. So it's going to avoid any point on here where x equals y. All right. Now we'll talk about a little bit of application of these, something called level curves, which is not really a big thing in calculus, but it's very good for like geology, specifically topography, looking at maps and sort of indicating how steep the slope is in mountainous regions and things like that. This is a hemisphere equation, half sphere, and upper half, obviously, square root, positive square root. So it's a half dome. And then what you do is this: if you set this equation to just arbitrary values of c, that would graph circles. And I just chose that. The choice of c is arbitrary. You can pick several ones. Now I just kind of went with 0, 1, 2, and 3, just kind of establish the pattern, and then you're graphing a bunch of concentric circles that are just inside each other. That's kind of round. It forms the edge of the sphere. Now what that tells us is, and you'll see we look at the graph a little bit. Let me zoom in just a little bit on this. The closer the lines are together, the circles are together, means it's going to be steeper slope at that point than it is when they're farther apart. It's going to be less slope. So kind of think about how a half dome works like that. It's going to be steeper at the bottom of the half dome, and then as you go up toward the center, it flattens out, and then obviously it has a flat slope right there at the very top of the dome. In fact, I went ahead and looks like I'm graphing the dome down here just to show you. Yeah, and then so there's the graph of that. And yeah, so you can see that these steeper circles on the outside means that slope is higher, and then as you get farther inside, there's the lines are farther apart, so the slope is becoming less and less and less as you go up. So if you're looking at a map, you can sort of see the closer the lines are together, you've got some steep kind of mountain ranges and things like that. They're steeper at the points with the closer lines together. So, all right, well, that's not super important for the study of calculus or anything, but I thought it's an interesting application. And here's where I just sort of have it. I didn't mention this before, but here it is in writing that, yeah, it works better. It looks better if you kind of choose values of C evenly spaced to give you a better idea. Like I chose 0. Now, of course, I'm not sure how Maple did it here. 12. It might have just picked 12 arbitrary numbers. I didn't enter them in here like I chose the values C here. So I'm not sure exactly how Maple, but I'm sure they evenly distributed the values for C. Okay. And this, once again, this is not important from a calculus standpoint, but it's an application in economics of a multivariable function called the Cob Douglas function that measures the number of units produced based on the number of units of capital X, and then the number of units of labor is X, capital is Y. And then it's kind of a little more advanced, and we need to worry about, what the C and alpha are. That's if you were really studying this seriously, you'd need to know that. Obviously, the example I'm going to show you here is already going to have those numbers in it, but that's beyond the scope of what we need in this class to figure out, what the alpha needs to be or whatever. But so one of them is going to be x to some alpha, where it's between 0 and 1, and then the y. So together, the two exponents always add up to 1. All right. Let's see. Yeah, here's one. Forgot where I got this example from. It doesn't matter. So it's telling you the number of units of labor is 30. That's X. The number of capital is Y, be 50. Find the total number of units produced when alpha equals 0.4, and C equals 100. So here's your C, 100. So X is labor, so it'd be X raised to the 0.4, and then Y would be raised to the 1 minus that 0.4, which is 0.6. And then once you have this function built like this, plug in whatever numbers are given to you in the problem. So here we were given a 30 and a 50. Obviously, we've got to put them in the right order there. So that's why the labor is X and the capital is Y. You don't have to know that. I mean, if I ever put this on a quiz, on an exam, not only would I give the formula, that I would also do, like I did on the last page, I would define, which one's X and which one's Y. You wouldn't be expected to know that. So really, this is just an exercise is, can you put the right number in the right spot and use your calculator properly? And I just rounded to the nearest whole number because I'm assuming that the total number of units produced has to be a whole number. I don't know how you would produce a fractional unit of something, but anyway, so I just plugged them right in there. Here they are in the calculator. Got 4,076. Excellent. And all right, well, that's it. That concludes this video for Intro to Functions of Several Variables.